Hello! Welcome to the underfloor air distribution chapter of this DVD. My intent is to provide you with the information you need to understand this innovative air delivery system. In this chapter, we'll cover the circumstances that prompted underfloor air distribution developments, how it works, some of the benefits it offers, some design and construction guidelines that make for successful projects, and we'll share some of the lessons we've learned through the years of experience working with underfloor air. Underfloor air delivery is a byproduct of the development of raised access floors. In the beginning, they were used primarily for data centers, computer rooms, and similar facilities. Human comfort was not a primary concern. As technology became an increasingly integral part of business, and the need to gain access to building infrastructure, such as electrical, phone, and data lines throughout the business environment grew, raised access floors allowed unfettered pathways to route and reroute cable. All raised access floors have removable panels supported by grids of pedestals of various heights. This grid and panel design allows easy access to the space in systems below, greatly simplifying reconfiguration of the space above. It wasn't long before construction professionals realized that the space below the raised floor could act as a duct. Technology and creativity met an opportunity to address the demands of contemporary business environments.
I guess what I like the most about the underfloor system is its flexibility. It's flexible, it is efficient, and its distribution is tremendous.
To understand underfloor air, we've found this very useful to compare it to traditional ducted mixing systems, something with which we are all very familiar. Overhead ducted systems are generally mixing systems with a lot of sheet metal and the labor to fabricate and install it. Occupying about 24 to 36 inches below the structure, they usually deliver 55-degree air at relatively high velocities through diffusers mounted high in the space. These systems push large amounts of conditioned air into the existing occupied airspace that is being heated by people, electronics, lights, exterior walls, etc. The job of a mixing system is to dilute that heat back into the space with enough cooler air to maintain the desired space temperature. The space air also contains contaminants, such as volatile organic compounds, or VOCs, from carpet, paint, adhesives, CO2, and skin cells from people, dust, dirt, pollen, and so on. The air provided for cooling is also filtered and provided with outdoor air so that the mixing of the overhead air into the existing warmer, contaminated air in the entire space allows the system to maintain the desired room temperature and a tolerable level of contaminants. Underfloor air distribution uses a space beneath the raised access floor, usually 14 to 18 inches, as a pressurized plenum, which contains 60 to 65 degree air. This plenum essentially acts as a duct throughout the entire floor plate. The plenum is pressurized to approximately 0.05 inches of static pressure and is delivered at lower velocities through floor-mounted diffusers. This smoke test shows conditioned air delivered low in the space. Underfloor air delivers the air in the first 6 to 7 feet of the space above the floor, which we refer to as the occupied zone. Above this point, the warmer air will rise out of the occupied zone into the unoccupied zone, where the heat and contaminants are allowed to stratify. There is still some mixing in underfloor air systems, in the first 4 or 5 feet above the floor, but not as much as overhead systems. Most of the warmed air and contaminants stratify high in the space, carried there by plumes of heat from all heat-generating sources in the space. Underfloor air distribution puts the conditioned air in the occupied space in the first 6 or 7 feet where it is needed, where the people are. If you think about the way heat rises off the pavement, or heat waves, that's an easy mental depiction of what happens with heat sources in a room. Heat will rise from the source, and if left undisturbed, it will rise out of the occupied space, stratifying near the ceiling. These graphics illustrate a typical temperature profile of an underfloor air distribution system and a ducted overhead system. The redder the color, the hotter the temperature. The mixing system is doing what it was designed to do, constantly mixing up the heat and contaminants in the space. The underfloor air system is allowing heat to stratify in the unoccupied zone, shown as a redder color toward the ceiling. You can see the heat plumes are more pronounced on the underfloor side of the profile, and that the conditioned air is more concentrated where the people are in the space. Engineers may be wondering, with 60 to 65 degree air, what about humidity? And wouldn't you need twice as much air? We'll save the latter for our discussion about loads, but here's how we handle humidity. Air is brought in through the return of the unit, mixed with outdoor air, and then cooled to around 55 degrees, removing the moisture from the air. The air is then mixed with return air from a bypass damper and then reheated additionally by the fan. We modulate the bypass air based on the relative humidity in the space. You would be very surprised to know that only 10 to 15% of the total CFM supplied is bypassed return air for bringing the supply air temperature up to 60 or 65 degrees at peak load. The load in the space is the same for an underfloor air system as it is for an overhead mixing system. The difference is in how we handle the load. Because we are only cooling the occupied zone and allowing the heat plumes to stratify out of the occupied zone, the amount of CFM is less or nearly the same as with an overhead mixing system. As you can see, the amount of load conditioned by an underfloor air distribution system is approximately 40% less than the overhead system. This is because we are not diluting the load back into the space, but allowing it to leave the occupied zone through its natural buoyancy to do so. Using the equation to determine CFM needed for cooling, in this case, yields us with nearly the same amount of air for either system. In some cases, this displaced load will be taken back to the cooling coil and will have to be allocated to the cooling plant. Otherwise, it can be exhausted from the building for further savings. In spaces with larger volumes, you may be able to allow the heat to collect in the unoccupied space and dissipate over time. It is important to point out that every space will have to be evaluated and the load calculated. As with overhead mixing, there are no rules of thumb or cookbook approaches that are safe to assume.
The culture of poor indoor air quality just went away. And we went from having calls and complaints on a weekly basis from people that were feeling ill, would get headaches, all those classic symptoms of poor indoor air quality, to a building where we really didn't get phone calls, and we really haven't had a problem since.
Here we have a similar graphic showing carbon dioxide profiles. As with heat, contaminants in the ducted overhead system are thoroughly mixed, keeping contaminants within the space for long periods of time. This makes the quality of the space and the return air virtually the same. With underfloor air supply, contaminants are allowed to stratify into the unoccupied zone. This stratification moves much of the CO2 and other contaminants from the occupied space into the unoccupied space and helps improve indoor air quality. The air from the unoccupied zone, which is of a higher concentration of contaminants than the occupied space, is returned to the supply air unit where air is purged and replaced with outdoor air and cleaned through filtration. Ducted overhead mixing systems, diffusers, and return grills are generally located high in the space, which may to some extent short-circuit some of the conditioned air back into the return, reducing the cooling and mixing effect. With underfloor air, it delivers all the air low in the space and returns it all high. As we said before, the air enters the space and is mixed in about the first 4 to 7 feet of the space, allowing most of the heat and contaminants to stratify into the unoccupied zone, where return air is drawn from. Now we have a pretty good understanding of underfloor air distribution and how it compares with traditional ducted mixing systems. Next, we'd like to point out what we see as some of the benefits derived from underfloor air.
The need for flexibility has been around for a long time, and this certainly speaks to that. The need for a responsible environmental attack and approach to energy savings that are real and tangible and can be counted on has obviously been increasing dramatically in the last few years.
The raised access floor, the underfloor plenum, and floor-mounted diffusers are the basis for some important benefits in these areas: tenant comfort and operability, initial cost savings, energy efficiency, and flexibility. No matter why a building is being built, tenant comfort and operability are always considerations. Underfloor air distribution has proven to be an exceptional solution. Underfloor air distribution maintains even temperatures throughout the entire space and uses simple to install thermostats that allow for tenant control in offices or other enclosed spaces. If by chance a diffuser is situated under a desk or some other undesirable position, it's simple to pull up a diffuser tile and exchange it with a full tile from a location more convenient for the diffuser. This is a major benefit in commercial buildings when tenant reconfiguration is required. Ducted overhead air often requires removing and replacing the rigid ducts, VAV terminals, and diffusers to suit reconfigured space use, which is labor intensive, not to mention the effort of doing this above a ceiling. With underfloor air distribution, the floor tiles are part of the HVAC system and are much more durable than typical ceiling tile. The swapping of floor tiles and diffusers is much easier and provides major cost-saving opportunities. Thermostatically controlled floor-mounted diffusers are daisy-chained with simple plug-and-play wiring connectors, so reconfigurations are much less complex than with ducted systems. It's estimated there can be savings of 58% over ducted reconfigurations. Furthermore, to add or change one HVAC zone, we've seen savings in the 22% range. The simplicity of these systems makes them easy to understand and maintain by building maintenance people. In fact, the chillers and rooftop equipment used are nearly the same as ducted systems. Underfloor systems can require fewer filter changes and have fewer moving parts than many overhead VAV systems, and commissioning and balancing these systems is greatly simplified. Underfloor air distribution allows for enhanced space utilization. Often, the interior height can be increased or floor heights can be designed to take advantage of the savings realized but not needing the 24 to 36 inches of overhead ductwork. People who experience a well-designed underfloor air system consistently comment on how fresh the air in the space seems. This is due to the stratification of stale air and contaminants to the unoccupied zone, while conditioned air is delivered where the people work. And these systems are very quiet. With the lower air velocities and greatly reduced ductwork, noise is simply not an issue. As you have seen, tenant comfort and operability benefits are really quite impressive. Now let's explore the initial cost savings to be gained with underfloor from the equipment and installation perspectives.
Probably one of the biggest savings is fan horsepower, because most of your energy in your system is lost in the delivery of the actual air. It's a fan motor. So with a displacement system and the underfloor air, we have a lower plenum pressure, so it takes less fan energy to deliver the air.
The initial cost savings when installing underfloor air are benefits important to every job we plan. When we exclude the capital cost of the equipment, we've experienced underfloor air numbers of $4 per square foot. We've all seen ducted overhead systems come in at $7 per square foot and more. These savings come from a number of factors. As you can imagine, there are substantial savings to be found regarding ductwork costs. The material and labor to fabricate the ductwork in overhead mixing systems is considerable. On-site, underfloor air delivers efficiencies. Experience has shown that a 300,000 square foot building with ducted overhead system can require as much as 30,000 man-hours of field labor. The same size building using underfloor air can be as little as 10,000 man-hours of field labor. That's a considerable savings. And as you can imagine, there are far fewer traffic jams and scheduling conflicts among the trades. Many developers find the ongoing energy savings the most compelling benefit of all. 20 to 30% energy savings have been experienced with underfloor versus overhead ducted systems. We know that fans use the greatest amount of energy in ventilation systems. With a floor static pressure of only 0.05 inches, the fan horsepower can be reduced by 30 to 50% over a ducted system, utilizing 1.5 to 2 inches of static pressure. This is why underfloor air has significant savings in energy usage versus conventional ducted overhead systems. The higher delivered air temperatures of 65 degrees allows for more economizer opportunity. That's when outdoor air is utilized for cooling. It's common to realize 250 to 350 more hours of economizer operation per year. By putting the cooling where the people are with underfloor air, the building can realize a 20 to 30% energy savings, which is significant now and will be even more so in the future.
It does simplify some things late in the job. The coordination above the ceiling is almost eliminated because you've gotten rid of all this large ductwork that's in the overhead space. So you're not trying to coordinate that with the fire alarm and the sprinklers and the lighting and all that.
Underfloor air is no different than any other system when it comes to following proper design and construction guidelines. We just need to be aware that they are different from that of traditional ducted systems. The qualifications and experience of the architect and engineers, as always, is critical to a successful project. The coordination between them is about the same, but they are dealing with different sets of issues. The same goes for the contractor and tradespeople. Qualifications and experience counts. Once they've installed a few of these systems, contractors and trades very quickly learn to love them. Underfloor air does require attention to new and different issues. Some of the design guidelines include floor height, shaft locations, underfloor partitions, an understanding of how air warms as it moves towards the perimeter of the space, how buildings lose heat, and perimeter heating systems. Underfloor systems require direct digital control systems, which is really no big deal. And the systems must be commissioned, so it's not quite like turning on a light, but the commissioning is simplified over comparable ducted systems. Experience has shown that plenum integrity is absolutely vital. Attention to holes into the plenum space must be addressed with care. To recap, here what we see are the driving factors why underfloor air distribution is worth considering. Indoor air quality is greatly enhanced over mixed systems. Occupant comfort is greatly enhanced. It's a much quieter system. Better space utilization is possible. The flexibility of reconfiguring the space is a big plus in today's office environment. Enhanced construction schedules due to reduced labor. Reduction of installed fan horsepower, which is a real dollar saver. And ongoing energy efficiency, which alone is probably reason enough to consider underfloor air. The bigger the building, the greater the savings. In many situations, the benefits of a properly installed underfloor air system are so overwhelming that it's worth adjusting our thinking to accommodate this innovative way of delivering conditioned air.